Hi everyone, how do we reflect graphs of functions? Let's look at y equals root x once again, the red graph. How do we reflect this graph about the x-axis so that the point 1, 1 goes to the point 1, negative 1, or the point 4, 2 goes to the point 4, negative 2? What equation will have a graph that goes to the green point here and the black point over there? How about y equals the opposite of root x? So notice we're taking the opposite of the right-hand side. We're multiplying the entire right-hand side by negative 1. If you have more than one term, you'll need grouping symbols. So in order to reflect about the x-axis, you multiply the right-hand side by negative 1. How do you reflect about the y-axis? That involves the S word, substitution. We substitute x with its opposite. I'll do this in blue. Y equals root opposite x. We take the red graph and reflect it about the y-axis. We do that with a substitution. We substitute x with its opposite. And what if we were to apply both transformations? What if we reflect about both the x-axis and the y-axis? Y equals the opposite of the square root of opposite x. In orange. We say that we're reflecting about the origin. We get from the red graph to the orange graph by rotating 180 degrees about the origin. So to recap, to get from the graph of the original function to its reflection about the x-axis, you take the right-hand side and multiply it all by negative 1. You take the opposite of the right-hand side. I'm assuming you have the form y equals an expression in x. To reflect about the y-axis, you do a substitution, that S word, substitution. We substitute x with its opposite. And to reflect about the origin, you do both. And that corresponds to a 180-degree rotation about the origin. So from the original purple graph for y equals root x here, you can get these various other graphs from reflections about the x-axis, the y-axis, and the origin. And these principles apply, of course, not just to the square root function, but to other functions as well. Now, again, a point plotting table can help explain what's going on. Notice that if we go from the graph of y equals root x to the graph of y equals the opposite of root x, if we go from the red graph to the purple graph, what happens to the domain and the range? Well, the domain stays the same, the non-negative reals, but the range is flipped upside down. And we see that over here, from y equals root x to y equals opposite of root x. Domain stays the same, non-negative reals, but the range is flipped upside down. Remember that for the square root function, the domain and the range were both the non-negative reals. Now, going from y equals root x to y equals the opposite of root x, okay, check this out. The domain for root x was the non-negative reals. But what's the domain for the square root of the opposite of x? It's the non-positive reals. And that explains why when you go from the red graph to the blue graph over here, the domain is flipped around. The range stays the same, but the domain is flipped around. The domain consists of the set of non-positive reals, 0 and the negative real numbers. So the domain is flipped around, but the range stays the same as for the original, the non-negative reals. Once again, if you understand what the graphs look like, then that can help you figure out domain and range. Once again, and this will help you out a lot in calculus because people forget this, the square root of the opposite of x is defined as a real value for non-positive real values of x. A lot of people forget that. And that's because the domain looks like this. The non-positive reals looks like that. By the way, there is a connection with even and odd functions. The graph of an even function has a property that when you reflect it about the y-axis, you get itself. That's because you have symmetry about the y-axis. Likewise, the graph of an odd function is symmetric about the origin, because when you reflect the graph about the origin, you get the original graph. And that's explained algebraically here. Don't worry too much about that. No, the symmetries, the even symmetry here about the y-axis, the odd symmetry here about the origin, but you don't have to go too much into the details of the algebra here. So far, we've been dealing with rigid transformations, like we're dealing with a piece of wire and we don't have to warp it. What if we're allowed to warp the wire, squeezing it and stretching it? Then we get to non-rigid transformations next.